In section 4.3, we looked at L'Hopital's rule. L'Hopital's rule is a really helpful tool used to evaluate limits that are of a certain form. And those forms are indeterminate forms, where it's not really clear where the limit is going because you got one guy going to zero, the other guy going to zero. So in this fraction, it's not really clear who's winning this tug of war. It also works when you have 0 times infinity. That is also an indeterminate form. It's not clear who's winning that tug of war. And we'll look at two examples highlighting these two structures. So here's number 15 from the section. We're taking the limit as x goes to 0. The first thing you want to do is plug in 0 into that expression and see if you get a nice number out of it. Plugging in 0 to the top, e to the 0 is 1. 1 minus 1 minus 0, that gives you 0 on the top. On the bottom, 0 squared is 0. So this is a 0 over 0 indeterminate form. The top going to 0 wants to take this whole fraction to 0. The bottom going to 0 wants to take this whole fraction to infinity or negative infinity. So there's a bit of tug of war. It's not really clear who's winning at the moment. So we can apply L'Hopital's rule. And L'Hopital's rule uses derivatives. So you can turn your original limit into this new limit, where on the top, you're going to have the derivative of the original top. The derivative of e to the x minus 1 minus x is e to the x. The derivative of negative 1 is 0. The derivative of negative x is negative 1. And on the bottom, the derivative of x squared is 2x. We can try to plug in 0 into this expression and see if we get anything nice. Plugging in 0 to the top, we got e to the 0, that's 1. 1 minus 1 is 0. On the bottom, 2 times 0, another 0 over 0, indeterminate form. So we can apply L'Hopital's rule once more. And this becomes a limit as x goes to 0 of the quotient of the derivative of e to the x minus 1 is e to the x on the top. The derivative of 2x on the bottom is simply 2. And for this guy, we plug in 0 to the top, we get 1. Plug in 0 to the bottom, it doesn't have any x's, so you stay with a 2. So the limit is 1/2. So this process works when you have limits involving the limit as x goes to a constant, and you have the indeterminate form 0 over 0. It also works when you have limits as x go to infinity or negative infinity. In this next example, let's look at the limit as x goes to infinity of x times the sine of 1 over x. Plugging in large values into these x's, x goes to infinity. Plugging in large values of x's to these guys, 1 over x, 1 over a large number, that goes to 0, and the sign of 0 is going to be 0. So you have a 0 times infinity indeterminate form. This element going to 0 wants to take this product to 0. This element going to infinity wants to take this product off to infinity. Whenever you have 0 times infinity indeterminate forms, you want to take one of these functions and rewrite it as 1 over its reciprocal. So if you have a function, you want to turn that into 1 over that function. If you're talking about a constant, let's say the number 5, would you agree that 5 is equal to 1 over 5? In fact, it is. Here's the benefit of doing that. We still haven't applied L'Hopital's rule yet. We're just making this expression look a little different from what it started off to be. So I took that x and I have rewritten it as 1 over x. This is the same thing as the limit as x goes to infinity of the sine of x on the sine of 1 over x on the top, and on the bottom 1 over x. Check out what happens when you plug in large values of x into this expression. For the top, if you plug in large values of x, that 1 over x goes to 0. and the sign of 0 is just 0. So the top is going to 0. And on the bottom, as you plug in large values into the x and 1 over x, the bottom goes to 0. So you have a 0 over 0 indeterminate form, the same kind of structure that we saw in the last problem. So this guy is a candidate for L'Hopital's rule. We'll apply L'Hopital's rule here, and this becomes the limit as x goes to infinity. For the numerator, we'll have to use the chain rule. The derivative of sine is cosine, right in the original argument, times the derivative of 1 over x, that's negative 1 over x squared. On the bottom, the derivative of 1 over x is negative 1 over x squared. These two guys cancel out, and as you plug in large values of x into this cosine of 1 over x, that 1 over x goes to 0. The cosine of 0 is 1. And that is our limit.